Welcome to this lecture on heat transmission by heat conduction. This is one of 3 lectures, so today we will talk about heat conduction. As the next subject, we will talk about thermal radiation, and we'll also talk about heat transmission by convection. And those things work together, as we can talk about also, and as we did in the introduction, but today will be the focus on heat conduction. Heat conduction we can have in different geometries, so we can also, for the geometrical system, we can look to a rectangular shape of the systems. We can have a cylindrical and a spherical. Today we'll cover only the rectangular issue here, but we'll also have a subject later on where we'll talk about the cylindrical. The spherical we'll not cover in this course here. Heat conduction, that's a mechanism for heat transfer which is taking place at an atomic scale, in a solid, in a liquid, or in a gas. So with the increasing temperatures, the vibration of the moleculars or atoms are moving to each other. So without being moved completely, there's no mass transfer. Well, then we have a conveyance of the heat transfer from warm towards a colder environment. And today we'll cover only one-dimensional heat flow. So that means that we have only a gradient in one direction. We don't have the gradients in other directions. So only a gradient in the x direction, not in y and z. So that also means that the next thing we do is that we look to stationary or constant conditions. And that means that after a while at least we'll have such conditions. And that means that we will have linear temperature profiles within our bodies that we're looking to. And then we can calculate the heat flow according to Fourier's law, which could be written here. So we need some parameters that we'll also talk about here in the lecture. So here is Fourier's law as it should be written by principle. So if we take a temperature gradient, because it's a temperature that is the driving force for the heat flow by conduction, and then we have a thermal conductivity lambda, which characterizes the material in which we have the heat flow taking place. Then, of course, the area of the wall is important also. So that gives us then the total heat flux. The total heat flow that we'll measure in the unit of watts. I said already, repeated here. So we have heat flow from high to low temperature, and that explains also why we have the minus here in Fourier's law. Because as you see here, if we have a declining temperature flow, that means we have a heat flow from left to right, which is a positive value in the x direction. So that's why we need the minus sign in front of it. So in a wall, then determining factors for the heat flow, otherwise it is, as I said before, the area of the wall, but also the thickness of the wall. The thicker it is, the more it decreases the possibility for heat flow. And then the characteristic of the material, the thermal conductivity, and of course the temperature difference over the material. So those are these characteristic parameters, and either we can have Fourier's law in a differential form, just as on the previous slide, or we can have it in a finite form if we have the absolute temperature difference from left to right side of the material and divide by the thickness of the material. That of course gives us our temperature gradient. So the thermal conductivity, by definition, you can also see here, it's if you have a unit form of material, 1 by 1 by 1 meter, and if you have a unit temperature difference across the material from one side to the other of 1 degree centigrade, well, then the heat flow that will be given under such conditions, that will be the characteristic for the thermal conductivity. And therefore, we have such values for different materials. Normally you look them up in tables, and here is such a list for a number of typical building materials. And the question has this posed up here on the top, which material do you think is the best suited for thermal insulation? Well, if you want thermal insulation, you want a small heat flow, so you want a material with a small thermal conductivity, small lambda value, and that of course is mineral wool, so the insulation material out of those that are given in this list here. So also we talked now so far about the heat flow in the unit of watt, but very often we talk about heat flux, and flux, that is the same value but only taken per area, so it's a specific value of the same. So flux Q is equal to to the phi value divided by the area A. So then we have, again, Fourier's law is written in this form, where we now write it in the terms of flux. What's also interesting here is to, again, of course, we use the thermal conductivity of the material, we use the material's thickness, but very often we have a certain material where we know the thickness, we know what it consists of, and therefore we would be interested to talk about what is the thermal resistance of this material. And that is 1 over the values we have up here, so the thickness divided by thermal conductivity gives us the thermal resistance of the material. And now we can calculate heat flux as temperature difference over the surfaces inside and outside, or exterior side of the material, divided by that thermal resistance will also give us our heat flux, watt per square meter. So now in order to calculate also for real constructions, we should consider not only the material, but also that we have conditions taking place at the surfaces. Here, supposing the exterior surface on the left, interior surface on the right, and that's actually convection and radiation, as we explained in the introductory lecture, that is the heat transfer mechanism at those surfaces. But for standard calculations, we also use a thermal resistance to characterize what are typical conditions for resistance for the heat flow from the exterior surface to the outdoor environment, as well as on the inside surfaces, what resistance you will have here. And here are the standard values for thermal resistance in those places. When we consider that, then we should consider the heat flow completely from inside to outside, so between those two environments, and therefore we should also take into consideration those two heat transfer resistances. And they come then down in the denominator. So we sum up all the layers we have, in this case 3 layers, we sum them up in the denominator here of this addition of still, in a way, Fourier's law. So yes, things come in series and we simply add them up. Now, so we have now begun also to talk about having several layers, but of course it could also be that we have several building material layers. So if we have different materials, different thermal conductivities, each of them will have their own thermal resistance given by their thickness divided by the thermal resistance. So therefore, by adding up all those layers we have in our construction, that would give us a summation of resistances as we were using in the formula up here on the top here for, again, to calculate the heat flux through our wall. So in this 2-layer wall, you can simply calculate R1 and R2 based on, as I said before, the thickness and thermal conductivities. So now we have the heat flow, but there's another characteristic we use for a complete wall, including its surface resistances. And that is the thermal transmittance of the wall. So how well it transmits heat through it. And that is 1 over the sum of those resistances we have now talked about. So the total resistance is the sum of all those layers, resistances, and 1 over the total resistance, that is our U value, as we call it in daily speak, but formally it's called the thermal transmittance of our wall. And here is how to calculate it. If we want a well-insulated construction, we want one that has a low U value, so a low thermal transmittance. Now, to have an example of how to calculate those things, we very often use in tables. You can, for instance, do it in a spreadsheet like Excel, where you list all the layers that you have in your wall. Remember the exterior and interior surface resistances, because those resistance values we should also take into consideration. Otherwise, we plot the thickness, thermal conductivity of the normal building material layers, calculate by taking thickness divided by lambda, calculate their thermal resistances, and in the bottom here, we can add up all to find the total thermal resistance for the whole construction. 1 over that value, that gives us the U value, the thermal transmittance for our construction. Here in our case, this example with a brick insulation and cellular concrete or lightweight concrete wall, a U value of 0.245. Watt per square meter Kelvin will always be the unit in this case. So the U value together with a temperature difference, here is also in the example given a temperature difference of altogether 25 degrees centigrade. And it's also said that the wall has an area of 12 square meters. So that means that in this case we can calculate the total heat flow through the wall being 74 watts. Let's consider a little bit more, just to say as one of the small extra topics in this subject here, there could be a kind of a layer inside of a wall, which could be an air layer. An air layer we have to consider, indeed we have also both convection and radiation, but very often in standard calculations we can calculate that simplified by using standard thermal resistances for that. And that depends on whether we have a horizontal heat flow or vertical heat flow. And if it's vertical heat flow, up or down, it depends whether it goes up or it goes down. And then it depends on the thickness of the cavity. So in this graph, you can have an easy reading of what would be the equivalent gas resistance of that layer, considering for practical conditions, convection and radiation over the gas layer. So then you can read a value very easily. It becomes more or less constant, not so dependent on the thickness of the air layer. But here's a way to read the value for the gas thermal resistance. So now we can add that also. If we have such layers, the total resistance of a construction becomes like before, all the material layers, exterior and interior surface resistance, plus possible resistances of air layers you might have in your construction. And so the last thing we would have an interest to do is to calculate a temperature distribution through our wall, so we can know what are the temperatures somewhere in the middle of the wall. And to do so, we use the mechanism to say that over a certain layer, for instance, layer number J, the temperature difference over that layer is the thermal resistance of that layer multiplied by the heat flux that goes through the wall. And the heat flux that goes through the wall, well, that is the temperature difference over the wall divided by the total resistance. So in this way, we are using the thermal resistance of that particular layer over which we want to know the temperature difference as a guiding parameter to say what fraction of the total resistance has this layer. And then that fraction determines how much of the total temperature difference between inside and outside that falls over our layer number J. So this proportionality between temperature difference and resistance of individual layers is the significant way how to calculate. So finally, I'll go back to the example again. So it's more or less the same as we had before, the same layers, the same resistances and such. But now I've added the temperature drops that come over each of these three real building materials layers and the exterior-interior surface resistances. So to take, for instance, for the exterior surface resistance, we have 0.04. 0.04 as a ratio of 4.075, the total resistance. Well, if we multiply that ratio with the total temperature difference of 25 degrees, we see a 0.25 degrees centigrade temperature drop over the exterior surface resistance. And so forth, you can calculate for all the other material layers in a construction. And such you can calculate a temperature value for each interface in the materials. Finally, you can check again that we get the same U value and heat flows and fluxes as we also saw earlier. So that kind of wraps up the whole thing about calculation for this class here about heat conduction. And for next, we'll also talk more in detail about convection and radiation. But this is enough for now. Thank you for listening to this.